In this section, we're going to talk about data organization and I/O paths. The question that we're asking is, how is data organized, placed, and located within the storage system? Pure uses a process called location addressing. In this process, their primary metadata construct is a key value store, a mapping table, that takes the LUN and LBA values and maps them to the physical location of the block data, the segment or offset that's been used. Of course, multiple keys can point to the same data in the case of a block that's been deduped. In addition to this, Pure uses multiple additional metadata structures. The first is a link table that keeps track of multiple keys pointing to the same data block from blocks that have been deduped. Second is the dedupe table, and this is an index of block checksums so that we can do quick, optimistic duplicate checking. The final one is a medium table, and this is really a directed graph that keeps track of shared block ranges between volumes, snapshots, and clones. All of the metadata in a Pure array is stored in SSD and is partially cached into memory, which is important to know that cache misses will hit SSDs if they happen. If we look at the Pure I/O path on the read side, Pure generates a list of LBA pairs using the medium table. They will then find the highest of those pairs to get the proper offset and then get the actual blocks before they return them to the user. Pretty straightforward. On the right side, incoming blocks are translated to the corresponding volume and LBA values, which are stored in the medium table. Pure will also attempt to do pattern matching at this point on those blocks in order to deduplicate them. However, this is not an inline process, as you can see from the graphic. Instead, this process will be run inline when it can be, and if the system is above a certain CPU threshold, it will defer the pattern matching until the next time garbage collection runs. Then, the blocks are persisted to NVRAM, and the write is acknowledged back to the user. To be clear, this is a very wise decision that Pure has made. In a dual controller architecture, where the CPU and RAM resources are fixed and limited, making sure that I/O is always handled and always processed before data services is very smart. Having the ability to defer those data services is a trade-off and frankly a feature that most customers would understand and appreciate. And the fact that there should never be a Pure array in production that's run at such a high level that CPU resources wouldn't be available means that this rarely, if ever, comes into play. From NVRAM, the blocks are written to SSD and the metadata logs are updated. Finally, that metadata itself is written into the pyramid and the write process is complete. SolidFire and Extreme I/O use a process called content addressing. In this process, the volume metadata is also a key value store, but the LUNs and HBA keys are mapped to a block ID, or a unique content fingerprint that's generated. Multiple keys can of course have the same content fingerprint in the case that they're deduped. Block metadata is a distributed key value store for the actual block data itself. In this case, we're mapping the block ID to the physical location of the block data. All metadata in both of these systems is stored on SSD and kept 100% in memory at runtime. If we look at the Extreme I/O and SolidFire data paths, we can notice some differences. For reads, the first lookup is to find the block ID and the volume metadata. This gives us the mapping of the block ID to the node. We then route that read request to the node responsible for the block ID. The location gets looked up in the block metadata, and the block is read from SSD. In the case of SolidFire, we decompress the block and we send the result back to the user. For writes, the block data is first hashed before anything else is done with it, and then for SolidFire, we compress it and then store the entire thing in NVRAM. Once the block has been replicated to a second NVRAM instance and is protected against power failure, the write is acknowledged back to the user. From NVRAM, the write is routed to the node responsible for the block ID, and the volume metadata is updated. Finally, the block itself is written to SSD, assuming it doesn't already exist elsewhere, and the block metadata is updated as well. In summary, there are two ways that this problem has been solved. The first is location addressing. In this case, the primary metadata allows for a single layer of redirection from the LBA directly to the physical location on disk. The storage itself and the physical storage locations are very tightly coupled to the metadata, and any move of data requires a metadata update. Also, a separate table is required to be able to handle the hint index for all deduplication functions. This is best for architectures where all of the metadata and the data are globally accessible by all controllers, which is something Pure does very well. The second option, content addressing, requires two metadata lookups, where we go from the LBA to the block ID, and then from the block ID to the physical location on disk. The physical storage is very loosely coupled to the metadata, and this allows much more flexibility and gives us the ability to move data around easily. Deduplication is an inherent part of the data placement process in this solution. It's really best for distributed architectures and for places where large-scale global deduplication pools need to be managed across a cluster of storage.